All right, let's talk about some concepts that I want to get through to finish our week out so that way we can have responsibly gotten that test retake done during class. So, last class we left off on the idea of expected value. Today we're going to keep leaning into that. And last time I had given this example of gambling and assessing whether or not a gamble was worthwhile or not. So one of the ways we had leaned into this was this idea of you're playing a game, and 5 out of 6 times you lose $20, and then 1 out of 6 times you win $100. And the way to assess whether or not this game was favorable to you was to use a law of large numbers type argument. So imagine you had thousands and thousands of dollars, so you could play this game over and over and over and over and over again. Well, after, say, something like 6,000 trials, 6,000 plays, you might expect that roughly 5,000 would be losses, which would mean in total you'd lose 5,000 times $20, which is to say you'd lose about $10,000. Get another zero in there. And then you would have roughly 1,000 wins, which is to say that you would win 1,000 times. Each time winning to the tune of $100, which would mean you'd be up about $10,000. Okay, so here you can see that in this game you should expect to break even in the long run. Okay, and this is the idea of expected value, is if you were to participate in something enough times, or if you were to have enough people do something, what is the average result you would expect? What is the outcome you would expect to be typical? And again here, typical is a little misleading because in no plays do you make $0, but in some sense, the common result is to get $0 out at the end. So let's dig into that just a little bit more and think about this differently. Well, one of the things that I'm relying on here, so I mentioned that law of large numbers. One of the things that I'm relying on here is this idea that at some point odds and frequencies are interchangeable. After enough observations. And of course, this is, again, not necessarily the statement of law of large numbers in its fullest formality, but a statement of the spirit of what the law of large numbers is saying. And this is what was going on up here. So I started with these odds. I started with the odds of 5/6 and 1/6. But then we converted this with a large number of plays, and I consider 6,000 to be relatively large. We converted this into counts. So we said, well, okay, law of large numbers says that if I play 6,000 times, roughly 5,000 of them should be wins, because roughly 5/6 of them should be wins. And then similarly, roughly 1,000 of them should be wins. And again, law of large numbers in fullest technicality says that we're not going to get exactly, or at least not very likely get exactly 5,000 and 1,000, but we're going to get something in that ballpark. So these words roughly are doing a lot of heavy lifting for us here. Okay, so using that law of large numbers idea, I want to think about what would an expected outcome be? What would an average outcome be if we have enough observations? Well, if odds and frequency are roughly interchangeable, really what we're getting, in the example I gave a second ago, the expected outcome of the game was, well, we took the number of losses, which was 5,000, times the value of losing, which was minus $20, and we added that to the number of wins times the value of a win. And again, we got 0 out of that. But we can go further than that and flip this back around to an odds statement. So I can instead say that 5/6 of the time I'm going to lose $20, and 1/6 of the time I'm going to win 100. Now the math here is just a little bit uglier, but if you're comfortable with fractions, or indeed maybe I'll just let the iPad drive it home, you get 0 there, and then of course it's going to do some silliness. But the point is you get 0, and one way you can see that is, well, 5/6 times negative 20 is negative 100 over 6. And then 100 times 1/6 is 100 over 6. And you wind up getting then that the result is 0 in either case. Okay, and this turns out to be the slightly more compact way to think about expected value, because unlike the frequency argument, which makes us say, well, it's probably about $5,000, and well, it's probably about $1,000, instead what we can do is say, well, no, I actually know it is, in the long run, exactly going to be this amount of money coming from losses and this amount of money coming from a particular win. So we can formalize that a little bit. We can make that a formula. If you have several outcomes, each with certain odds, then the expected value of a process that ends in one of those outcomes is, well, the value of the outcome, so we'll call like the first one outcome 1, times the odds of outcome 1, plus the value of outcome 2 times the odds of outcome 2. Here I'm excising the word outcome just to make things a little bit more compact. And then this would go on until you get however many values you have. Slightly more formulaically than this, if xi are values of outcomes, and pi are odds of those outcomes, expected value is outcome 1 times its odds plus outcome 2 times its odds, all the way up to the last outcome, which we'll call outcome n, times its odds. In your textbook, I think they even give you the fancy summation notation, which looks something like that. So all three of these things, this more verbal way of saying it, this more algebraic, and then this is like slightly fancier, using what's called summation notation way of saying things, are all ways of calculating the expected value, and they all hinge on this idea of finding an expected outcome, which ties in nicely with some of the stuff we've seen with law of large numbers earlier in chapter 6 rather, sorry. So that's expected value. And I will motivate one sort of application question, and then we'll move on from there. Suppose you are playing a game where what are the words I'm looking for here? Suppose you're playing a game where you flip a coin. Maybe let's even have it be flip 2 coins. If you get 2 tails, you get 1 point. If you flip a heads and tails, and we'll make it in either order just to reduce some of the headache, you get 2 points. And if you get 2 heads, you get 3 points. Or alternatively, you can take 1.5 points with no flipping. And your intuition would probably say that you're on average better off flipping coins, and we'll try to put some math to that in a second. But I do want to at least observe that there is at least notionally a chance that the alternative is worse, because if you flip the coins, you could wind up getting 2 tails. Now, of course, the thing with expected values is, on a given flip, there's maybe more importance to being consistent versus doing well, or vice versa, and in which case expected value maybe isn't what you're going to do. Let's say you're playing a game with a lot of turns, you're early in the game, and really all you care about is accumulating some points. You really just want to know, okay, on average, is flipping coins better or worse than just taking my 1.5 points? Well, we can use expected value to figure that out. The odds of flipping 2 tails out of 2 coins is 1 out of 4. And then, again, thinking about our formula for expected value, we multiply that times the value that we would get in that 1 in 4 chance. The odds of flipping a heads and a tails in either order is actually 2 out of 4, or if you prefer, 1/2, and that's going to be times 2 points here. And then the odds of 2 heads is again 1/4. We're going to multiply that by 3. And if you add this all up together, you are actually going to get a 2. And so you can see that on average, you are better off flipping coins than you are taking the 1.5 points. Now, again, this is on average because you could always wind up in the situation where you have flipped 2 tails. But if you were going to play 10,000 rounds of this game, you would be far better off consistently choosing to flip 2 coins than you would to just taking your 1.5 points. And so when you are making decisions where you have lots of attempts at the decision, or you're making a decision for a large aggregate of people, so for example, you could conceive of an instance where a government is making some decision which is going to cost some citizens money, but give money to other citizens with some sort of probability. You could see where a government might actually care about an expected value approach to things, because an expected value approach would maximize the total amount of money made per capita, while it might cost some citizens some money. Now, of course, realpolitik is such that depending on which constituencies might lose out, that might not be the decision you make. But my point here being, expected values are useful for making large decisions in aggregate, but maybe not always beneficial in particular instances. So for example, if you're guaranteed, it's the last turn of the game, and 1.5 points is all you need to win, and you're guaranteed to win to take the 1.5 points, the fact that on average flipping 2 coins is worth more to you is completely irrelevant to the facts of the situation. So again, this is this contrast between long-run value and the value in a particular situation, which is something that, hopefully you were thinking about in all sorts of situations in your life. Okay, there's one other thing that I want to talk about with this idea of law of large numbers, and then we should be sufficient to wrap for the week. And this is this idea that we can turn observations on their head. So what I'm going to set up is this idea of a sampling distribution, and we're going to use that to start thinking about hypothesis testing, to start thinking about whether or not some default assumption holds in the face of evidence. Like we talked about last week, the dependency of that is ultimately always going to be due to chance. And so what we need to start doing is figuring out what the chances of making certain observations are under certain assumptions. So let's suppose we know that in a room of, this is 5 by 4. So in a room of 20 people, 16 like blue and 4 like red. You know this is a fact about the room, but your friend, let's say, doesn't. So your friend has this question. Do more people like red or blue? Okay, natural question. Here's the catch. They only have time to ask 3 people. And admittedly, the situation's a little bit contrived. You could probably just ask people to do a quick show of hands. There are probably lots of ways you could get around this. But in real statistical scenarios, you wind up with a situation kind of like what your friend is faced with, where you want to know something about the population, in this case, whether people like red or blue, but you could very easily imagine that this was some political conversation instead, or some economic conversation. It could even be that you're doing market research and asking do people like Coke or Pepsi more. There are lots of ways in which you can imagine a question like this is actually something somebody would have find critically important to know the answer to. And you can imagine that instead of 20 people, you've got 2 million people, and that getting everybody to talk to you is going to be very difficult. So maybe this idea of only having time or resources or access to a limited number of people is more reasonable in certain contexts. Here, we're boiling it down to something that's a little easier to get our hands around, but I want you to see that this is actually, like, with very little stretching, analogous to something that you might find in a real statistical study. You've got a question about a population, and you want to ask 3 people. Now, the thing that we're going to do is, as people who have total knowledge of the room, we're going to ask what are the odds your friend actually makes the correct observation. So, what are the odds your friend finds more people like blue? Okay. And the thing is, because you and I know what the population looks like, this is something that is somewhat accessible. So one of the ways we can do this is we could try to count, using purely theoretical methods, what are all the ways we could sample 3 people. And I'm actually going to use my highlighter here to talk about this. So you could imagine, for example, that your friend asks these 3 people just by random chance. And you can see that that observation counts in favor of them finding more people that like blue, because from their interpretation, maybe even everybody likes blue. And the more people like blue, that would be 1 count in the column, and so far we would have none. You can also conceive of a situation where those 3 people are asked what they think. And you can see that that's going to happen. Now, of course, there are actually a lot of possible samples here. So, for example, these 3 people would, which would still be a mark in favor of the yes camp. And as you might expect, I would have to do this for a long time to actually count. There are fancier formulaic techniques, and again, if you dig more into statistics, you might actually learn some formulas for figuring this out. The thing that I want you to see, though, is that this problem is tractable. Like, if I sat here for long enough, I could figure out what every possible grouping of 3 people would be. So, one of the groupings I would get would be these 3 people. One of the groupings I would get would be these 3 people. One of the groupings I would get would be these 3 people. And all of those things are conceivable samples that we could get. And one of the questions I can ask is, well, how many of them have 3 blues in them? How many samples have 2 reds and a blue? How many samples have 3 reds? How many samples have 1 red, or 2 reds and 1 blue? And from that, I could then recover my answer to this question by just asking, well, how many samples have 2 or more blues in them? What you probably won't find surprising, given that there's so many more blues than reds, the odds that your friend finds more people like blue are pretty high. And this is one thing that I want you to see, and one of the reasons why I was saying sometimes those formulas aren't necessary. This is something that you could easily feed a computer. You assign each of these dots a random number, or not even a random number, you can assign them sequential numbers. You have a computer draw 3 numbers at random out, and you have it repeat that process, say 5 million times, which again, for a computer, wouldn't take very long to do, and you just have it spit out a frequency table, where on one hand, you have a blue count, and actually I want to flip this, I want to put the blue count on the other side. On the other side, you have a frequency. So as you might intuit, getting 0 blues is going to happen with relatively low frequency. So let's say out of 5,000 simulations, the frequency of getting 0 blues is going to happen something like 250 times, let's say. The frequency of getting 1 blue is again going to be relatively rare, but more frequent than getting no blues. The frequency of getting 2 blues is going to happen something like 3,500 times. And then the frequency of getting 3 blues is going to happen, let's say, roughly 750 times. Now, I'm inventing these numbers based off of the vague idea of the sort of distribution this would follow. But again, from law of large numbers, after 5,000 simulations, I can pretty much turn these into odds. I can pretty much say that the odds of 0 blues would be 250 out of 5,000. I can pretty much say that the odds of 1 blue would be 500 out of 5,000. I could pretty much say that the odds of getting 2 blues would be 3,500 out of 5,000. And then again, I could say the odds of getting 3 blues would be 750 out of 5,000. And so then, turning back to our friend's question, the odds that our friend would find more people like blue would be roughly 4,250 out of 5,000, which is approximately equal to, let's see, is it going to save the day here? %. It's going to be approximately equal to 85%. On the flip side, one of the things that I want you to see is thinking about that idea of significance level. If your friend observes instead that more people like red, well, that shouldn't be too surprising, because that should happen 15% of the time. And 15% of the time is something that happens. Every day you experience something that occurs only 15% of the time. And it's a very, very common level of observation. And so one of the things that we might conclude here is actually asking 3 people whether or not they like red more than blue is maybe not enough for us to have high confidence that we actually know whether or not more people like red or blue. And this is one of the things we want to start talking about quantifying, and that's where we are going to go next week.